Neil deGrasse Tyson, one of the most famous astrophysicists of our time, has once again challenged what we think we know about the universe, and this time, his focus is on Neptune, the distant blue world that orbits at the edge of our solar system. For decades, Neptune has been described in textbooks as a cold, quiet, and predictable ice giant, a planet made mostly of frozen gases, with fierce winds and massive storms swirling endlessly across its surface. But according to Tyson, that picture might be far from the truth. Recent discoveries, new telescope data, and improved simulations are revealing a side of Neptune that could completely rewrite what scientists have believed for nearly 2 centuries. Tyson explains that Neptune is not the calm, icy world we've been taught to imagine. Instead, it may be one of the most dynamic, mysterious, and misunderstood planets in the entire solar system. To understand why Tyson's claim is so shocking, we first need to revisit what we thought we knew. Neptune, the 8th planet from the Sun, was discovered in 1846 through mathematical predictions before anyone had even seen it. It quickly became known as the ice giant, alongside Uranus, because it was thought to be composed mainly of frozen water, ammonia, and methane. Its mesmerizing deep blue color, caused by methane gas absorbing red light, gave it a peaceful and serene appearance. But beneath that beauty hides something far more intense. Tyson notes that Neptune's winds are the fastest in the entire solar system, reaching up to 2,100 kilometers per hour, faster than the speed of sound on Earth. The planet is constantly battered by giant storms, including the famous Great Dark Spot, a massive system once larger than Earth itself. Yet despite these extremes, scientists long assumed they understood Neptune's basic composition and structure, until now. Neil deGrasse Tyson points out that new data from space observatories and computer models suggest Neptune may not be the simple ice giant we once thought. The planet's core, for example, might not be made of the solid rock and ice mix scientists expected. Instead, some evidence hints at exotic materials, substances that behave unlike anything found on Earth. Deep inside Neptune's immense pressure, methane molecules could be breaking apart, releasing hydrogen and forming what scientists call diamond rain. Imagine that, diamonds literally falling through Neptune's atmosphere like sparkling hailstones. Tyson emphasizes that if these processes are real, they challenge our entire understanding of planetary chemistry. It means that Neptune isn't just a static ball of frozen gas, it's an active, evolving world where extreme physics is constantly at work. Even more puzzling is Neptune's heat. Despite being nearly 30 times farther from the Sun than Earth, Neptune emits more than twice the amount of energy it receives. In other words, it's somehow generating its own heat, but how? Tyson says this internal furnace could mean that something deep inside Neptune is releasing energy in ways we still don't understand. Perhaps it's radioactive decay, leftover heat from the planet's formation, or some entirely new form of internal convection. Whatever the reason, it breaks the rules of what scientists thought ice giants could do. And here's the twist: Uranus, Neptune's near twin in size and composition, doesn't release the same heat at all. The two planets, almost identical on paper, behave completely differently in practice. Tyson calls this one of the great unsolved mysteries of planetary science. Why are Uranus and Neptune so similar in appearance, yet so different inside? Another revelation Tyson highlights is Neptune's bizarre magnetic field. Unlike Earth's magnetic field, which runs roughly along its rotational axis, Neptune's is wildly tilted, almost 47 degrees off-center, and even offset from the planet's core. That means the source of its magnetism might not come from the same kind of molten core that powers Earth's. Tyson explains that this strange behavior could indicate that Neptune's interior is layered with materials that conduct electricity in unexpected ways, perhaps a vast ocean of superionic water, a state of matter where hydrogen ions move freely through a solid lattice of oxygen atoms. This kind of matter doesn't exist naturally on Earth, and its discovery would redefine what we know about chemistry and physics under extreme conditions. But Tyson's biggest point isn't just about Neptune itself. It's about what Neptune tells us about planets everywhere. If our model for Neptune is wrong, that means our models for hundreds of exoplanets, distant worlds orbiting other stars, could be wrong too. Many of those exoplanets are Neptune-sized or slightly larger, and astronomers have been using Neptune as a baseline to understand them. If Neptune's structure, composition, or evolution turns out to be very different, it could mean that the entire class of ice giants behaves in ways we've never imagined. That's why, Tyson argues, understanding Neptune is not just about one planet, it's about rewriting the rules of planetary science. Tyson also reminds us that Neptune has only ever been visited by one spacecraft, Voyager 2, back in 1989. The iconic images it sent home, of swirling blue clouds, white storms, and a deep cobalt atmosphere, gave humanity its first and only close-up look at the planet. But that was more than 3 decades ago. Since then, our technology has evolved dramatically, and so has our curiosity. Tyson advocates for a new mission to Neptune, one equipped with modern instruments capable of scanning its magnetic field, studying its weather in real time, and probing its atmosphere to understand what lies beneath those hypnotic clouds. He believes that Neptune could hold answers not just about our solar system's past, but about how planets form throughout the galaxy. Another fascinating point Tyson makes is about Neptune's moon, Triton, a strange, icy world that might actually be a captured object from the Kuiper Belt, a region of frozen debris beyond Neptune. Triton orbits Neptune in the opposite direction of the planet's rotation, something no natural moon should do unless it was caught by gravity after forming elsewhere. Tyson says that Triton's backward orbit and active geysers of nitrogen gas might offer clues about Neptune's gravity and history. If we can understand how Triton became Neptune's moon, we might also learn how other planets capture or lose moons, and even how early solar systems evolve. What makes Tyson's revelation so powerful isn't just the science, it's the message behind it. He reminds us that science is not a collection of final answers, it's a journey of questions that evolve with every new discovery. What we once believed about Neptune was based on the best information we had, but now, that information is changing. And with it, our entire view of the solar system must evolve too. Neptune, it turns out, might not be a silent frozen world at the edge of space. It might be a restless, active, mysterious planet with forces and secrets we are only beginning to uncover. In Tyson's words, every time we think we've figured out the universe, it humbles us. Neptune is humbling scientists today. It's reminding humanity that even in our own cosmic backyard, there are worlds we barely understand. With its tilted magnetism, stormy skies, hidden heat, and shimmering diamond rains, Neptune challenges our imagination, and invites us to look deeper, question more, and never assume we know everything. Tyson's revelation isn't just about Neptune, it's about the spirit of discovery itself. Because in the end, the greatest mystery isn't what's happening on Neptune, it's how much more there is still left to discover.